Thank you very much for the possibility to be here. First of all, I will show you what I did this week, and where I was really stressed because we organized a big workshop on Wednesday with our shared control guys, how I call them, and it's a big team from many different countries, from UK, Netherlands, so most of our Europeans, and we met here in Singapore. And I said, oh no, we have to travel to Singapore to meet, although we are all of our in Europe. But it was a really great experience. It was really great to see the culture, and it was also a really great conference. And it's a great pleasure to be here in Singapore. So thank you very much for the possibility, and thank you very much also for the possibility to hold this talk. That's the reason why I'm not so prepared as I would love to have been. So please excuse for the small mistakes if you find something. And today I'm going to talk about our research, what we are doing at KIT. And we are designing models. So we are creating models, formal methods using mathematical models to describe human-machine interactions, which can lead you to trustworthy and safe human-machine systems. We are at KIT doing research for the society, and what our goal is to serve the humanity, serve the people. And it's KIT doesn't do any military research. We don't do any to harm people, to serve people. That's our goal, and that's what KIT stands for. It's a very big university with many different faculties. So we also have human science faculties and history faculty. You never heard about that. There are not many of them, and physics and engineering and many different studies. The interesting in KIT that it started as a university Karlsruhe back to 1825. And Karlsruhe is a very young city. It's more young for Europeans. It was founded in 1715. So, and around 100 years after the first university, where big names like Benz, like many of the German engineers spent some time in Karlsruhe. So it has a very rich history. It's funny if you are going to Max Planck lecture room, or where is Max Planck lecture hall? So it's a big history. And in Karlsruhe there was a research center, Karlsruhe. So that was two different campuses, and it reunioned in 1928. And after that it became from Technical University Karlsruhe and Research Center Karlsruhe one big institute, KIT. That's how we got together, and we are able to do now more and better research in a big university. It has lots of benefits, lots of challenges as well. And while lots of happened in the last years, and we have also a new vice president and presidents in the last years. And we have lots of campuses. We have 6 campuses. 1, 2, 3, 4 are in Karlsruhe. And there are 2 others which are not in Karlsruhe. We are also part of the Helmholtz Society. Helmholtz Society brings people together, not people, universities together to work together on different topics. So it's a really great network to work together. And we are in the campus south. It's in the heart of the city. So I really love it. It's really green. It's really close to everything in Karlsruhe. So I really love work and live there. And our institute, IRS, stands for the German version, Institute of Regelungs- und Steuerungssysteme. In Germany, in English is Institute of Control Systems. And we have 2 main buildings. And we work in this villa. The funny thing with the villa, it used to be the living residency of one professor back to in the 60s. So one big professor lived in this building. So I also telling my students, hey guys, you know where I live. So If you have problems, knock me on the door. And it's a really old and nice building where we work. There are 3 full professors in the institute. Oh, the lines are not very good. And my professor is Professor Hohmann of the control systems, and I'm leading the cooperative systems. And what we do in the cooperative systems group, you can check it out for the link, what exactly we do. And we designing human machine systems. We're designing robotic systems which can support and which can help human doing their work. I have seen some of your research and I thought about, okay, you can fully automate it, but you can also use human machine solutions, and sometimes our human machine solutions more sustainable, or it's easier to deploy. Yes, some of the colleagues do very theoretical research. So these 4 of them are doing very theoretical research. And there are also practical applications of our research. What we are doing many optimal control and games. So we are doing differential games where you have many optimization problems, but you will see later in the upcoming slides. And who I am? Well, I'm Balint Varga, and I came originally from Hungary. So I was born and raised in Hungary, and I did my bachelor in Hungary in mechatronics. And after that, I went to KIT to do my master's in mechanical engineering. And after that, I had the possibility to start work in a research institute where I decided, okay, let's go for the PhD. In Germany, PhD a little bit different because you are a research associate, you do research work, you work on projects, and during that time, you have the opportunity to do your PhD. So you are not a student anymore, you are basically a lecturer, you do projects, you are writing proposals as a PhD student. So you have different responsibilities than in the States or in the Netherlands. And that's why I started as a research associate, and during that time, I decided to do my PhD. Yes, I worked as a developer at Knorr-Bremse in the Research and Development Center Budapest for 1 year, just during and after my PhD bachelor thesis. And I worked as a research assistant and research associate at FZT Research Center for Information Technology. And in 2020, I went to KIT for different reasons, and I've been there since 2020. In the academia, I'm trying to be as active as I can. I'm really active in the IEEE Society's System Man and Cybernetics, where I'm co-leading the technical committee of shared control. Shared control means the control is shared between human and machine. So you have a shared control. You can imagine driving a vehicle with a machine together. And that's what we are doing there, how to design shared control systems. I'm also serving as an associate editor in the Transactions and Human Machine Systems and the International Journal of Robotics and Automation. And I'm serving as an associate editor in many conferences. I was really happy because in this conference, I get the best award for the best associate editor of the conference. So it was a really nice surprise. Yes, and but maybe I see your papers and associate editor and I have to handle it in the future in some of the conferences as well. Let's see. And what motivates me in my research and why I'm doing research and why I'm not doing boring industry job, because I can start from the very basic idea from the equations and get the field demos and build prototypes. That really inspires me to go to the field, to build prototypes and do innovation. And I really hope that I will be able to sometimes have a startup with motivated young researchers and do something impactful for the society. Yes, the very first questions, what you would ask, why shared control? Why do we need somehow a more general view of technical systems where the human also is involved? we have systems which became more complex, and technical systems also includes many different applications. Think about your home. Think about your smartphone for simple to a complex system. Think about autonomous vehicles or drones, unmanned aerial vehicles, or many other applications. It's a roadside cleaning vehicle in Germany that's a mobile robot at IRAS. And this is one of our projects, what we are working on, how to help elderly people in their elderly situation. And the question is, well, are full autonomous systems driven by generative AI, ChatGPT, and is it safe? Are they safe under uncertainty? What if you have human in the loop? If there is a human who deals with you, who's there and do something, and how you can handle conflicts if you have conflictive situations? What do you do there? And do you trust your AI-based controller? Are they hallucinating? How can you verify the learning effect of that? And many other questions which is addressed in a different way. So you may have AI systems which are verified. We are going from the other way. We say that we looking at these problems as a control engineer and system engineering problems. So we create models. We using cross-disciplinary expertise to design models, and from these mathematical models, we can create trustworthy and safe to deploy systems. So we can explain everything which happens there. We can explain why the controller didn't work, and it helps you to deploy the system safely and more trustworthy. I will provide you a short introduction to shared control, what it means. Then I will present you some practical projects, what we are doing at KIT and with Obuda University together. And finally, you get some of my visions, what I'm working on currently on my habilitation. And I'm really happy if you can provide some feedback for me. So why shared control? Yes, you have lots of systems where human and machine interacts, like autonomous vehicles. The vehicle is traveling, try to communicate somehow with the human, or assistive robotics. And as I mentioned, we are leading the technical committee on shared control. And I think that's the most important thing, that also in the societal challenge roadmap 2030 of the Control Society, IEEE Control Society, had a chapter on cyber physical human systems. So they also acknowledged we have to address the issue how human and machine can not only coexist in situation, but can live together in a harmonic, symbiotic way. That's the goal, to design safe systems. So what is shared control? Shared control means that you have a system where two or more parties distribute the control and collaborate and make decisions together. It means that you have the system and the classical automation, create an automation, you have some references, and you control the system, describe it closed loop, open loop, you have different control concepts. We say, well, the human can also control the system or some parts of the system. And it means that you have to design the automation in that way that it takes not only the system into account, but the human as well. And the goal is to have a cooperative and non-conflicting behavior. So you can design an automation which can control the system perfectly. But if you don't take the human into account, it can be non-intuitive, conflicting, and not easy to use system. Just think about your smartphone. If the application is not very intuitive, you won't use it. Or think about your lane keeping assistant or your adaptive cruise control in your vehicle. If it doesn't do the thing what you would like to have, then you don't use the automation. So taking human into account is very important. And the easiest examples are the vehicles, because I suppose most of you drive here in Singapore. No. Okay. 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 It's easy to say in Germany because in Germany everybody drives. Okay, you never use adaptive cruise control. Okay, maybe that's not the best example. But why we do that? As a human, you have a knowledge of the domain and the context of our decisions, so you can provide a more sophisticated reasoning in the situation. And the machine is very good at repetitive task, precision, and you can enforce safety limits. So yes, that's what I also always bring, the lane keeping and adaptive cruise control. You have to come to Germany and you have to try these systems. It's a honest invitation. If you want, come to Germany. And we have lots of applications in wheelchairs, shared control wheelchairs, within different countries. Okay, so you have the basic idea, system, automation. Well, it's a system, man, and cybernetics, so that suits very well to the society. And what we do here, we said, well, we need a formal model to make the system verifiable, understandable, and for that we use games, differential games. In the game, you have players. The machine and the human is treated as a player. They play together, and their decisions have an impact on the underlying dynamic system. Think about optimal control. You have your cost function, you have your underlying dynamic system, you optimize it, any methods, ADP, or you have different methods to optimize it. And the basic idea is the very same, but you have more than one player. So the solution of that optimization problem becomes more complex. So you have a coupled optimization problem, not a single optimization problem, like in optimal control. And the very same, you have the automation and the human cost function. And the optimum of that optimization is a so-called Nash equilibrium. It's an optimum in which you cannot deviate from that unless you will decrease the optimum of the cost the optimal cost of your cost function. So you have to optimize both cost functions, and the human cost function is given, so you cannot design it. And our goal is to design the automation in that way that is good, trustworthy, and safe for the human. And that's what we do. So we have the cost functions and we have the underlying dynamics. And in our research, we address many challenges. So if you have different references, what you do that, how to resolve that problem, or if the human adapts, you can also have different concepts for that. And that's also one of my research, the adaptive systems. So we want to make the automation in that way that it adapts to the human, but not using black box AI models, but using differential games and using the mathematical basis of differential games. You can assume that the human changes over time. You get more tired, you are frustrated, you learn to use the system or teleoperation system. Think about that, for example. And the goal is that the automation adapts to this human variability. So at the very beginning, you are very precise. At the end of your shift or end of your work, you are not so precise. You make mistakes. And in that, you can describe it as a variation of the model parameters. Again, go back. Okay, optimal control. Everybody's there. Optimal control. You did optimal control. Who never did optimal control? Okay, so but you know what is a linear quadratic? In MATLAB, you have the LQR, and you got something from that. And we can change the automation parameters to adapt the human, and we have to solve the optimization problem online, and using that online optimization, we can adapt automation. And for the adaptation, we we can use the adaptation for personalization. So if you have do you have an experienced driver, experienced operator, you need less support. And we are applying that, for example, for medical systems, for surgeons. And if they are at the very beginning of their shift, they are energetic and they can do their work very precisely. And during the time in their shift and the last hours, they are not so focused, not so concentrated. So the automation can help them to increase the system safety. And what do we need for the automation? We have to estimate. We have to estimate what the human does, what the system reacts, and based on that, we have an additional feedback loop which provides for us a learning. So it learns the parameters of the human and adapts the parameters of the automation. And the funny thing, it has a similar structure in reinforcement learning. And if you do model-free reinforcement learning, you have some similar aspects as we do have here, because you get always feedback from your environment. And we have shown that human variability respecting optimal control, which takes the human into account and his decision and his variability on online adaptation, can improve the task performance. Yes, and I moved on in my PhD research to the very special class of the differential games, the so-called potential games. You may think, well, okay, what is that? What does it mean? And the idea is, well, if you want to solve that coupled optimization problem online, it can be really complex. So let's replace that original game with one single so-called potential function, which can describe the original game in a simplified way. So we have the original system and we want to simplify it into one big potential function. And the optimum of that potential function should also lead us to the Nash equilibrium of the game. So it simplifies the problem and it makes the system more applicable for adaptive systems. And the question is how to find this potential function, how to find this suitable potential function. To be honest, in my PhD, I didn't find a good answer for that. That's the honest answer. I'm still working on that. I have undergrad students working on the so-called near potential differential games. And many of my ideas didn't work. So I'm really sorry for that guy. But still we have some applications where we can apply that because it increases the computational efficiency. It can be applied to multi-agent system in general. And you can ask the questions, okay, I presented the differential games, potential games. Why do we need models? Models we need because we want to explain the system. And if you explain the system and we have a model-based design, we can be trustworthy, we can safe, explainable, trustworthy. So that's the core idea behind it. Okay, that was, I hope that not too much theory. You are still with me. And I would like to show some of the projects, what we did in the last years. Sorry for these abbreviations. They are German ministries, German institutes where we get the money from. So it's the different German ministries. We work lots of with automated vehicles. And what I said, the cooperative driving. We were investigating what's happened if you steer, the steering wheel not alone, but with the automation together. Think about the situation, you have a full autonomous vehicle and the vehicle tells you, okay, now we are switching back to full manual because I cannot control the system anymore. And it can be really dangerous, this switching phase. And we proposed a transition phase that full autonomous, full manually, that you need a transition where you drive the vehicle together. So you have a higher situational awareness, you have a safer system, and for that we use models. Yes, we did lots of teleoperation in the Mars projects. There was a DLR, developed robots for Mars, and we were responsible for the human-machine interface and teleoperation. We also have, yes, Germany autonomous vehicle projects, how an autonomous vehicle should interact in the mixed traffic scenario with pedestrians, with other vehicles. We do have basic research projects and also healthcare projects and micro-mobility projects, how autonomous cargo bike can use in post service, for example. So in a delivery, you don't have to sit on the bike, but it follows you. These were our, yes, in the past projects. I would like to highlight one of our projects on fire brigade search and rescue mission. We developed a drone at KIT, an indoor drone, which was able to get in the building and find a person, missing person autonomously. For that, we use radar, because if the building is dark, smoky, you cannot use laser or cameras. And it was able to navigate autonomously without a predefined map of the building. And it was able to geolocate the persons. And so the fire brigade didn't have to get in the building and to find the person, but they only had to get in the building to get the persons out. So they saved time. If nobody's there, they didn't have to get there. And what was the original idea? The fire brigade, no, the original project was we build a full autonomous systems. And this turned out, after discussions in the fire brigade, we don't like that. I want to click there, I want to do that, I want to do that, and okay, we need a semi-autonomous system. So what we did, the leader of the mission was able to click on the graphical user interface and was able to provide the high-level goals, because they know where they want to go, and if they want to rotate or see something more precisely, they were able to override the commands. But the drone was fully autonomous between these points. So what we developed here, a method which was able to avoid local minimas and which was able to run on a very small NUC computer on the drone. So we had to take into account the computational power as well. And we had a modular system with the GUI and the ground station where the fire brigade interacted with the so-called limit ellipsis control navigation. And we used the Pixhawk, and we had some onboard AI systems to detect the persons. Yes, it was really interesting. I learned a lot because we set up all of the low-level controllers. I don't recommend you to set up low-level controllers. Have the right people for the right task and collaborate with your colleagues. I didn't have any colleagues there. I had somebody from some other tasks. I think it's also very important learning for an institute that you know the competencies and you work based on your competencies together. But we learned how the system worked, and it was also a really great experience for me. And that was the result. So the person was able to click there, and all of the navigation between the points was fully autonomous. And what you can see, these are the ellipses which were calculated based on the point clouds, and it was a dark room, so the visual camera wasn't able to navigate properly. And we also used a thermal camera, which also helped us to find the missing persons. And we used also geolocation to have the firefighters know, okay, where they should enter the building, this entrance, from the back, on so on, on so on. It was a really nice project. Regretfully, we were not able to continue. Politics, finances, and so the drone is not functioning anymore on our lab. That's also a pity. But that's German system isn't. Well, I can tell you later on a bit more. We had also really nice projects on autonomous vehicles. let's imagine the situation, you have autonomous vehicles in the city center. And if you interact with non-autonomous vehicle in the city center, they are slow. You look at the driver. You communicate with your eyes with the driver, and if the driver look at you, you feel yourself safe. You are trustworthy. And that was the issue. Okay, what if we have lots of autonomous vehicles and you have lots of vulnerable road users, so pedestrians, cyclists? How you can increase the acceptance of the society? And we addressed that with many German companies. And what we did, and what was my role there, we designed a new pedestrian model to predict and interact at the same time. So it was a empirical mechanistic model. And we have shown in a demonstrator that we were able to address the fundamental challenges of that interaction. We had also some publication on that. And it's also a very important thing. If you want to work with humans, and if you have human in the loop, you also have to think about the human factors aspect and the wording of the human factors. And I think that's why VW, Volkswagen, is one of the best cars, because they have lots of human factors engineers looking at the system, designing the system, and it was really interesting to see how it works. And this is our final demonstration. And maybe I only show one of the scenarios. So where you cross, the people standing there, yes, that was, he communicates with the arm. That was also a limitation of the camera system. It wasn't able to see the person rightly. And instead of using the eye contact, it was fully autonomous vehicle, and it communicated through a visual panel. So that was the way. It was also human factor engineers who thought about, okay, how you should use that part for the communication. What is the signs, what you're sending the people, and it means, okay, I'm crossing, I won't stop, please do not cross. Or if you have a pedestrian crossing, you can see, okay, you have the blue line. Oh, I have seen you, I'm stopping. That's the message is what it's sending, I'm stopping and I'm waiting. So it's like you're looking at the pedestrian and you can be sure that it will stop. We had some newer project currently. I would like to highlight one of the medical robotics projects. We do have it one company in Germany, and we have a really interesting standing up project. It means cooperative standing up A system. It helps people to get out of bed in a cooperative way. And the idea is behind that, you could build a bed which brings you up, and that's it, and you are standing. But in that case, you are not training your muscles, and you have illnesses where it's very important, for example, MS, multiple sclerosis, that you use your muscles, that you don't lose your muscles. And it's a system which enables a negotiation. If you pull more, it helps you more. If you pull less, it helps you less. So that's what Julius develops in his PhD, the negotiation between human and machine, how you can describe it with different models. What we do have in our lab as interface, we don't have so many nice things as you have, but we work pretty much with this haptic interface. We use the KUKA robot as a 6-dimensional human-machine input to investigate different human-machine interactions. We also have a motion capturing systems to get data and to learn how the human moves, point-to-point motion and different motion. Yes, I summed up my colleagues' research. It's maybe I can send you the slides later on. It's really dense. What we do optimal control, but inverse stochastic optimal control. You have a stochastic system, and you don't want to solve the optimization problem, but you look at the measurement data, and from that you want to estimate the cost function. So you do the inverse way. That's one of my colleagues doing that in my group. So I mentioned negotiation in the cooperative system. So how you can negotiate references. I have one colleague, he just presenting his first publication, IFAC 2026. He investigated gradient play in differential games. It's turned out there are no model-based method for that. So yes, you have lots of AI-based method, but using a model and describing the Jacobian spectrum with mathematical tools, it's not there yet. So he's just writing his transaction automatic control paper and the IFAC paper, and hopefully a control letters paper in by end of the year. Some more practical research, we investigated how the human variability should be taken into account by cooperative motions. And we are doing we started the inverse stochastic optimal control with one player. And if you have more than one player, you have inverse stochastic differential games. So you do the same thing. You want to identify the cost function of your optimization, but you do the inverse method of that. And how I get here, I'm also working with Obuda University, and we have a really nice cooperation. We are sending students here and there, and it's really nice. And we are focusing there also how to design human machine systems using the Da Vinci Research Kit. And what you can see is the device from the small Canadian company, Happily. Have you heard about Happily? You have heard about, okay. It's a really nice small company. They providing really nice devices, but you don't have all of the software. So in our current paper, we have written a bridge to Da Vinci, and we conducted some simulation and feasibility runs on the real device. And what you can see here is my students using a hot wire experiment. So you want to go through along the wire without touching that, and you can feel the force feedback if you are getting closer to the wire. So that helps you to maintain the distance to the wire. And it's turned out, yeah, the haptic feedback helps, and it can provide you feedback, increase decrease the time of completion, and it's a useful tool what we should investigate. Yes, and I ask the questions, are we going to need human machine systems? And if you talk with some other engineers, they will tell you, no need for that. We have full automation and they are more superior. Yes, you have some applications where you don't need human machine systems. We work with a factory. They are providing papers, Heidelberg Druckmaschine, and there is no human in the factory, just machines. On the other hand, yes, you need. And I was asking the questions, well, your grandma is alone, far away. Would you trust a fully AI-driven humanoid robot to take care of your grandma if you don't get any elderly care in the region? Maybe some human machine system, teleoperated system would be the answer for that. And that's what we're investigating currently with Tamás and Professor Heidegger and Professor Galambos at Obuda University. What we should do, yes, it's with the company. What we are working together with SAIS. We worked on the cataract operation. Luckily we get one publication, but we had lots of other works from the last 2 years we weren't able to publish. Yes, and we are investigating what kind of robot-assisted applications you need. There are lots of concepts in the literature, but they are not safe, trustworthy, and deployable. And that's what we are working on, that how to move to the field, how to make them deployable. And that's why you need models. That's what you need, models to have the certification from the, yes, to get the certification to deploy. And also the questions, we have teleoperations since 1980, and with Tamás from Óbuda, we went together and we were in a workshop, ERC workshop, in European robotic workshop, robotic conference, and we had lots of discussions. Well, you have 6G, you have 7G, and the question is it a solution? Won't you have some human in the back who teleoperates the system? And which is the bottleneck after that? So how you have to design systems that you can use for a longer time, how to switch between vehicle controlling. You are operator controlling 10 vehicles in Seattle, in Silicon Valley, how you can make it safe in a good way. And we've just published a paper in ICRA, teleoperation bottlenecks from the network-centric rather to the human-centered design, and how to design it. And I really hope that we can do lots of research on that topic, and I really hope that we find some common topics on that. These human-machine systems teleoperation, I'm really open to cooperate, and I'm really thankful to Peter Galambos, who is the PI of the Horizon projects where you are also involved, and I really thankful to being here, and thank you for the opportunity to present.
Great, thank you.